this promotional run. And it was subject to the constraints of budget and the requirements that we had for making 150 of each one, but it was a mix of products kind of a model. And that's what we're going to be doing here, product mix, and we're going to do a super simple model first. And the reason is because we're going to be introducing another new thing, another new tool, and so we're going to do a super simple model because when we use something that's really small and really simple, it's more intuitive, and we'll get the basics of how it works before we move it into using something that's larger than that, using something that's larger. So we'll be working our way through the model, using Solver, and then learning that new tool, which is a tool called Solver Table. So with our linear programming, with our optimization, we know that we have an objective. We talked about that before. There'll always just be one objective: maximize or minimize something, most likely maximize profit or revenue, minimize cost. I mean, last time it was maximize the quantity of the rackets, and then we have constraints. We can check the non-negativity box so that our changing cells are not, non-negative. The constraints are these inequalities or equalities. Seems like a lot of times there are inequalities because we're saying, we have to use less than or equal to what we have. We have to, so we had that. We know that the changing cells are the ones that Excel is going to fill in for us based on all that we're trying to do, the goal we're trying to reach, and the constraints that we have on it. Okay. So the solutions we discovered last time could be feasible or not feasible. Okay, we had something that was not feasible. They could be what's called unbounded, and I discussed that before. Like if you were trying to maximize and you didn't put any limitations on things, then it would just be trying to maximize to infinity. That would be an unbounded solution. There are some other things that we can do that will cause unbounded solutions as well. But the optimal solution that eventually comes out of this, that Solver chooses and says, this is your optimal breakdown of Model 1s and Model 2s, or breakdown of the products we're going to do today, occurs at a corner point. What that means, I have to get my good numbers out because they're nice round numbers that I'm going to use here. Their stuff is going to look nicer in the book, but anyway. Let's say you had Model 1 and Model 2 as something, it's not the tennis rackets, and it goes through testing and it goes through assembly. Because I think this is something like the example they explain this with in the beginning of chapter 3. And what are we up to? So if you look at your Model 1s, they take 2 hours for testing, 12 hours for assembly. If you look at your Model 2s, they take 5 hours for testing and 6 hours for assembly. And if you had, my good numbers up here, 500 testing hours available to you in total and 1,200 assembly hours available to you in total, we could actually plot this when we just have 2 dimensions like this. Let me get some stuff up here. All right. So what does it mean? What is LP programming doing? Well, this is what it's doing. First of all, let's look at, I'm going to plot some lines on this chart that are going to show us feasible and infeasible ranges of what we're working with here. We'll start with the testing. If you know that a Model 1 takes 2 hours to test, and you only have 500 hours available to you for testing, if you made all Model 1s, how many Model 1s could you make?
250.
You can make 250. If you look and you see Model 2s take, and this is my Model 1 axis, and this is my Model 2. They take 5 hours. You have in total 500 hours available to you. So if you only made Model 2s, you can make how many? 100. So this line, get it on there, it's not going to be all that straight. That line is the line that's telling you anything below this, any combination below this is feasible, any combination above this is not feasible. Now granted, I realize these aren't all, wouldn't all be full numbers, but that's the feasible range with respect to testing, right? I did that one first. Okay. So let's just look at assembly. If you had assembly, Model 1s, they take 12 hours, you have 1,200 hours. How many Model 1s could you make if you only made Model 1s?
100.
What? Yeah. Model 2s take 6 hours. How many Model 2s could you make if you only did Model 2s?
200.
Right. So now you have a different line going here. That's your feasibility for the assembly, okay? And, you know, you can just do like that, right? So anything below that line with respect to assembly is feasible, anything out here is not feasible. But because you have both constraints on here, and we're not gonna go past trying to do 2, I don't think in your book they do either, but anyway, this is the feasible region if you take both constraints into account, okay? So when that thing says the optimal solution is always at a corner point, what would happen, and we don't have an objective function on here right now, but our objective function would be, you know, maximizing the profit of Model 1 plus Model 2, whatever profit for times Model 1 plus profit for Model 2, maximizing it. Anyway, we could do a whole, lay out a formula that we could plot as a line, okay? And an equation that we could plot as a line. And that line, it would be our objective, our objective function line. As it went out, the profit would be getting higher, 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 higher. And so if it's sloped kind of like this, the highest point it will reach and still be feasible is that corner right there. If it was sloped a little this way, it might be that the higher, you know, the highest it could reach would be this point. Or if it was sloped a little that way, the highest point it might reach would be this one. In other words, that's why it says it always occurs at a point. It may not matter to you, that may not matter a lot to you. They are gonna explain this in the textbook also, because our linear programming solver model is going to work for us and just tell us, but that's what they're referring to. So this gets way more complicated when we start having way more constraints. And it's not then easy to put on a graph and show what it is we're dealing with at that point. And so, you know, that is what they're talking about there, but, you know, whether or not that's ever gonna, you know, if you feel confident about what you're using in the tool, you'll probably not have to think too long and hard about that. Okay. But the thing is, after we solve these things and we come up with, this is the best mix, and we did that with the tennis rackets. This is the best mix of Model 1s and Model 2s to give us the maximum number of rackets, given all the constraints that we had. And we kept adding constraints, which kept reducing those numbers, but we kept adding constraints. In reality, when we start to work with these models, we don't want that to be the end game. We don't want the very last thing that happens is, well, there's our plan. Boom, make this many of each of these products. Or if we have a lot of products, make this many of each product. And the reason that we don't want that to be the end result and just stop is because so much of what we do when we're modeling has uncertainty involved in it. We are working with demands that are probably uncertain. We may be working with other things that are, you know, predictions of what something might be. And if we're working with things that are uncertain, which would be the real world, you know, real things that happen, then we want to always go back after we've created a model and look at the sensitivity of these different outputs to what if things changed about the inputs. Okay, so we want to do more than just stop and say we're done. Okay, we want to do sensitivity analysis, and we have found that data tables are a really good way to do sensitivity analysis. You know, we did that on the NCAA t-shirt thing. What if these were the order quantities and the actual demand amounts? You know, what would happen? What if I ordered less and the demand was more? What if demand was less and I ordered more? And, you know, so we did what if. And so that's the kind of thing we're gonna get to here too. We're gonna do sensitivity analysis on our problem afterwards. But we're gonna introduce, excuse me, we're gonna introduce a whole new tool. It'll take us a couple minutes to do because we'll all have to install. Okay, so this example right here, this is our, like I said, our uber small example so that everything will make sense and be very intuitive when we are learning this follow-up tool, okay? We're gonna print and sell t-shirts. We sell them, the ones with the, you know, color ink on the shirt for $15, the one with just the black and white shirts for $10. We purchased the blank t-shirts for $5. The color is layering different colors, and so the ink costs $1.50. The black is just one layer of ink, it costs 50 cents for the ink. It takes us to layer and print the, the ink, it takes us longer, so it takes 4 minutes to do the color shirts, 2 minutes for the black and white shirts. We have 8 hours available to us on whatever machine it is that does the printing. Okay? And we have $1,000 available in cash. And that right there is everything we need to know to optimize this problem. We know what we're trying to accomplish, which is to make the most money, what we sell the shirts for, what they cost us, okay, and how much time and money we have to try to accomplish this. We have everything we need here to do it, to do what we need to do. So we're gonna do that, and then we'll answer all the other questions about, what's the profit, what's how many shirts should we make, how much money do we make, what's binding, and then we will get to the sensitivity analysis on this one, and that'll take a little bit. We will not do example 2 and the computer tech, PC tech problem until next time. Okay, so right now, we're just gonna do this first example, and it seems like it's a really small first example to do, but we're gonna stretch it out, because we're gonna really understand everything by the time, we're done with it, hopefully, that's the idea. So, all the numbers that you saw on the PowerPoint are here. The selling price, the blank t-shirt price, the ink prices. We're going to need to calculate the cost per shirt, the time it takes to print. We know that the thing we are trying to solve for is the appropriate or best breakdown of how many of each type of shirt to make the most possible money. So those are our changing cells. That's what we're gonna let Excel tell us, just like we did with the rackets. That's what we're gonna let Excel tell us. But because we know that we are limited in time and money, it will be necessary for us to calculate how much time we're using in order not to exceed what we have, calculate how much cash we're using in order to not exceed what we have, okay? Now, I will say, you were told that you had 8 hours. You were told how the shirts were made in minutes. One of these two had to be converted, okay? Don't care what you had to put everything in hours, everything in minutes. You could have made this decimal hours if you'd wanted. I mean, that's fine. But instead, we just decided to convert this one to minutes. You're gonna have to. You have to do that in order for this to work. Okay. All right, let's start with the easy stuff. What's the total cost per shirt of producing a color shirt? The cost to you is what? By the time you've purchased everything you needed.
The blank shirt price plus the ink price.
Yeah. So those are the only two things you're even told that you pay for, and that's the shirt itself and the ink that goes on it, okay? So this shirt costs you $6.50, and the black and white one costs you $5.50. Okay, now, again, we have to calculate. I know there aren't numbers in here right now, I get that. But in the solution process, in the process of running Solver, Excel will be putting numbers in here. They have to, work into our whole solution. We've got to calculate how much time